Okay, I'm very happy to announce Ishan Levy from the University of Copenhagen. He will tell us about Malle's conjecture for function fields.
Thanks very much. Yeah, it's great to be here. Yeah, I was an undergrad here, so it's great to be back. Well, not at the IS. So, in fact, I think I only came here once or twice when I was an undergraduate ever. Maybe it wasn't good. Okay, so yeah, I want to talk about Malle's conjecture for function fields. And I mean, what I really want to talk about is Hurwitz spaces, which are a natural family of moduli spaces in algebraic geometry, which also play an important role in a lot of problems in arithmetic statistics. And Malle's conjecture is really just a segue into maybe why you should care about Hurwitz spaces. So to start the discussion of Malle's conjecture, it's really some kind of more precise version of something that might be more familiar, which is the inverse Galois problem. So the inverse Galois problem, it asks the following thing. So if G is a finite group, and let's say I look at a number field like the rational numbers, then does there exist a G Galois extension of the rational numbers? That's the question. And, we still don't know the answer to this question. There are a lot of cases where things are known, and Malle's conjecture sort of goes beyond this, and it asks a more statistical question about how many Galois extensions there are of this form. And so there are only, if you fix a discriminant, there are only finitely many number fields of that discriminant. And so Malle's conjecture tells you, if you bound the discriminant, how many asymptotically, how many of these G Galois extensions should exist. So it says the following thing. So conjecture by Malle around 2004. And it says that it predicts that the number of G Galois extensions of the discriminant less than or equal to x, when x is large, it should be upper and lower bounded by a constant times the function that's x to some power, and then log of x to some power. And so there's some constants. There's some constants a, and there are some constants that depend on the group, a and b. And there's some explicit constants that you can define. And the conjecture is that this is sort of the growth rate of the number of G Galois extensions when you bound the discriminant. Yeah. So, we don't know how to prove this in general, but there are a lot of cases where things are known. So, for example, when G is abelian, this is known, this has been known for quite a long time. And maybe another case to point out is when you take G to be S3, S4, or S5, this is essentially the work of Bhargava's thesis. So, there are a lot of things, so there's a lot of work on this problem, but we don't quite know it in full generality. And so I want to talk about the function field setting where you replace Q with FQT. And by doing so, you obtain a lot more geometric tools to attack the problem. And what I want to talk about today is essentially that we can completely solve the problem maybe when Q is sufficiently large and you're only considering tame extensions. So so before I say what the statement is, I need to point out that there's some subtleties in Malle's conjecture. And that's because the original version of the conjecture is actually false. And so there's examples due to dinner. Let's see if I get the spelling correct. Okay. Which is from 2005, which says that if you take, you can take, for example, G to be Z mod 3 squared. You take this Reith product, which is the semi-direct product of Z mod 3 squared with Z mod 2. And for this group, the specific A of G and B of G that were predicted by Malle are not correct. And in fact, and I can tell you from the function field perspective why that's true. It's because, so in the function field perspective, you're counting Galois extensions of this form. And the point is that, geometrically, this corresponds to some finite cover of P1. And the more natural thing to consider is to consider, so these are sort of covers of P1 that are connected. But the thing that's more natural to consider, and the thing that does actually agree with Malle's original conjecture, is to count geometrically connected covers instead of just connected covers. And so the issue is that the connected covers that are not geometrically connected, in this example, they correspond, they sort of dominate the counts of how many G Galois extensions there are. And so that's why the prediction of Malle originally is a little bit too small. Okay, so there's work of Tur-Kelly, who essentially understood this point, the fact that sort of you really want to, the original statement of Malle is a little bit unnatural from the function field perspective, because you really want to be counting something more like geometrically connected covers. But Tur-Kelly sort of understood how this worked and made a prediction. About what the correct constant for this B should be. So about B, and so there's some other constants. I'll denote BT, T for Tur-Kelly, which is some other constant which is it's larger than, at least the same as that. So there's some other constant where you might hope that this conjecture is true if you replace this B with that B.
These counter examples specifically to the function field analog.
Right, so it's also false in the number field setting for the same group. But actually, there is something that is quite different in the function field and number field setting, which is that it turns out that Tur-Kelly's prediction is still incorrect in the number field setting. So this is so Juya Wang very recently as counterexamples in the number field setting. To Tur-Kelly's prediction. And so
the A part is supposed to be okay?
yeah, so the A part is correct. Yeah, that's right.
Well, I mean,
And I can tell you what the A is actually. So it's something like one. It's something like the order of G times 1 minus 1 over the smallest prime dividing the order of G. Something like this. I hope that's correct. Yeah. And then yeah. And so that one's correct. And so right. So in the number field setting, even Tur-Kelly's prediction is incorrect. And there's sort of a lot of recent work going into saying what should be the correct the precise statement in the number field setting. And so the theorem I'm going to tell you today is that actually in the function field setting, Tur-Kelly's prediction is correct, at least when Q is sufficiently large. So let's write that down. So theorem, so everything I'm talking about today is joint work with Aaron Landesman. Yeah, and feel free to ask questions. So our theorem is that, this conjecture is correct when Q is sufficiently large. So if you fix G and maybe take Q to be sufficiently large depending on G. And maybe you also want Q to be relatively prime to the order of G. So we're only looking at tame extensions. And then if you look at the number of G extensions of Qt of discriminant less than or equal to x, then again, this goes, it's upper and lower bounded by a constant times x to the 1 over a of g times log of x to the Tur-Kelly's prediction of what b should be. Okay.
Are there counterexamples to the original thing for G simple?
Be simple. I don't think it's known, but I could be wrong. You know?
We're going to say that the nature of the Tur-Kelly modification is such that it should be the same always if G is simple.
Yeah.
So certainly not in the function field case because of
The Tur-Kelly.
and I don't think there's any kind
So
of
it's like Julia Wang's example is also some kind of wreath product.
yeah.
And yes, I don't think there's counterexamples Yeah.
In the number field case.
in either's case.
Yeah.
Yeah.
I agree. Yeah.
Okay. Okay. Thanks for the question. So any more questions about the statement or anything? Okay, maybe what I'll say is that there are a lot of variants of this theorem. This is sort of the most basic version, but some variants that you can prove are, instead of counting by discriminant, there are other ways you could count. For example, you could count by the number of ramified primes. So you can count by a more general invariant. And then we can still prove this kind of result. Another generalization is instead of working with just G Galois extensions, you can fix a permutation group, so an embedding of G into a symmetric group. And then you can look at extensions with respect to that embedding. So, there's sort of a version for permutation groups. Maybe another version is that we can also count geometrically connected covers, which is the more natural version of Malle's conjecture. And then the last one, say, is that we can also count G covers with specified ramification type. So you can fix some collection of conjugacy classes and say that you only want to look at G covers where the ramification is in that conjugacy class. You can fix ramification type. Okay. So, right. So how do we prove something like this? Yeah.
Sorry, when you say the discriminant less than or equal to x,
Yeah.
I guess, do you mean I guess shouldn't the discriminant live in FQ adjoint T?
So I want the discriminant to be Q to the degree of the ramification divisor.
Oh, okay.
Okay.
Thanks.
Yeah. Okay, thanks. So how do we prove something like this? So, I mean, the strategy that it really goes back to Ellenberg and Venkatesh. And I guess maybe that's for geometrically connected covers. And then I think Tur-Kelly thought a little bit about how to do it for connected covers that are not geometrically connected. So the strategy to Ellenberg Venkatesh
In Westerland.
in Westerland, is that right? Okay. Thanks. Okay. And so the strategy roughly goes as follows. So you're trying to count G covers of FQT. And what you do is you relate this question to counting FQ points on a certain moduli space called a Hurwitz space. And the point is that you can interpret these kinds of G covers as points on a certain moduli space. So you sort of relate this to counting FQ points on Hurwitz schemes.
Wearing high courtesan.
Yeah.
Published by Tumblr.
Oops, sorry. No worries. Okay. So then how do you count FQ points on Hurwitz schemes? Well, you know, these are they're smooth schemes over FQ. And so there's this Grothendieck-Lefschetz trace formula that says that if you can understand the Étale cohomology of Hurwitz schemes, then you can, and maybe the Frobenius acting on that, then you can figure out the number of FQ points. And so via the Grothendieck-Lefschetz trace formula. So not sure if it's worth writing that down. If someone's interested, you can tell me. So then this turns into a problem about understanding the Étale cohomology, the L-adic Étale cohomology of Hurwitz schemes. And now these Hurwitz schemes, they admit nice compactifications, and you can use those compactifications to relate the Étale cohomology to the singular cohomology of the version of Hurwitz schemes in characteristic 0. So you can relate this to singular cohomology of Hurwitz spaces. And so at the end of the day, you're trying to understand something about, you know, how many points are there on these Hurwitz schemes, and you sort of only care about how many points there are as, you know, as the discriminant gets large, which is sort of number of branch points gets large. And so you want to understand something about the cohomology of these Hurwitz spaces as the number of branch points gets large. Okay. Any questions about that? Okay. So I want to tell you now what Hurwitz spaces are. So the setup I want to use for Hurwitz spaces is I want to take G, be a finite group, and I'll take C, be a subset of G that's a union of conjugacy classes, maybe discriminant union of K conjugacy classes. Okay, these are conjugacy classes. And here is what the Hurwitz scheme is. So for GC, so it depends on this data, and it depends on a collection of natural numbers and 1 to nk. And it's B points where B is some ring, some test ring, is going to be the degree and covers of A1 over the base B with inertia. So remember, sort of the monodromy should be in C, and inertia is actually in Ci and I times. So there are Ni points where that's true. And then you also want to add the data of a trivialization. this G cover, sorry, not degree n covers. What I meant to say is G covers, okay, with inertia in C. So you have a G cover of A1, the monodromy, it's branched at some finitely many points, and the monodromy is in C. And then you also want the beta of a trivialization at a boundary point. There's also a version without this trivialization, but this trivialization makes it into a scheme, a smooth scheme, as opposed to a Deligne-Mumford stack. Okay, so that's the scheme whose FQ points count G covers of some sort, and so that's why it sort of relates to that question. And again, we're interested in really the complex points of the scheme, because ultimately the singular cohomology is going to tell us something about counting FQ points. And so what we want to do then is let's just call her G, C, and N1 to Nk. I'll call that the complex points of that. So in other words, it's a space where the points of the space are given by some configuration of points in the disk, and then a G cover. And then you have a trivialization at some boundary point, and then the monodromy around each of these things is in this union of conjugacy classes, and it sort of appears this many times. Okay. So these are the Hurwitz spaces. And okay, so there are a lot of different ways you can start to think about Hurwitz spaces. So there's a lot of structure on Hurwitz spaces, and somehow from the point of view of homotopy theory, they're really nice spaces, and they're quite natural to consider. And so here's one alternative description of Hurwitz spaces. So first, what I'll say is you can take the union over all n1 all the way to nk of her GC n1 nk. So these are non-negative. So I'll just call that her GC. So here it's just a union of components, and you're allowing as many branch points as you want. And so when you do this, this is actually a topological monoid. So this is a monoid. And the reason is because you can take two G covers with the trivialization, you can concatenate them. And so that's sort of a fundamental piece of structure on all of the Hurwitz spaces put together. And there's another way to describe what this monoid is, or what this total space of the homotopy equivalence is. So another way to think about it is the following. So you can take the union over n at least greater than equal to 0 of, you take the set, which is n tuples of elements of C, and then you take some kind of quotient by an action of the braid group. So it's really a homotopy quotient. But for example, the components of this Hurwitz space are exactly if you just took the orbits of a braid group action on this set. And so what is the braid group action? So the braid group action is the following thing. So if I have two elements in C, X, and Y, then I need to tell you what a braiding does to them. And what it will do is it will send it to Y inverse XY. Okay. And so this tells you what that generator of the braid group does, and that extends uniquely to an action of the braid group on n tuples of elements. And then you can take the quotient. So.
But where is G?
Sorry?
In this description, there's no G.
Right, so G was sort of implicitly used in whatever this conjugation means. And so really there is a way to set this up where G was not actually relevant in the construction. It's sort of just C with some additional structure about what it means to conjugate. And so there's this, so there's some more general settings in which you can talk about Hurwitz spaces, in which you can prove all our theorems. So there's this word, there's this notion of a rack, which is with the setting that we actually all prove our theorems in, which doesn't involve a G.
Thank you.
Yeah. So, okay, so there's this comparison map from these Hurwitz spaces to a configuration space of points. So this is parameterizing some kind of G cover, and you can just forget the data of the G cover and just remember the sort of ramification locus, the points at which it was ramified, and that will give you configuration of points on a disk. So, and maybe if you remember which conjugacy class it is in, they'll sort of be colored. The points on the disk will be colored by how many points are in each conjugacy class. And so there's a map like this that it's actually a finite cover. So this map's a finite cover, and if you do it algebra geometrically, it's a finite étale cover. And this union, I'll just call it con to give it a short name. Okay. So anything else I wanted to say about that? Okay. Oh, maybe one more thing I have to say. So, we're not really interested in these problems. We're not really interested in counting arbitrary G extensions. We really want to understand connected G extensions, or maybe geometrically connected G extensions. And so there's a sub-scheme. It's just a union of components inside. So there's a, maybe I'll just write it over here. So there's a sub-scheme, which I'll just write here, called C-Her GC. And this is counting cover. This is the space that parameterizes covers that are connected. So the total space is connected with the cover. And so this just ends up being a union of components inside the whole Hurwitz space. Yeah. Now I can state the theorem. So the theorem is that we can, if you let the number of branch points get really large, then the homology stops depending on the number of branch points. And moreover, we can say exactly what the homology is. That's roughly what the theorem says. So the first theorem is our homological stability theorem. Which says that if okay, so it says that if you fix G and C, then there exists I and J, which are positive numbers, such that if Nj is at least I times I plus J. So if the number of branch points is sufficiently large, then you have this map, which is, it's the map from the ith homology of this connected Hurwitz space, where you have n1 to nk branch points. And now what you can do is you can do homology with integer coefficients, and then you can concatenate by a cover which only has a single branch point. So you can choose some element G inside C, and you can concatenate a cover with just that as a single branch point with that monodromy. And so that's sort of multiplication by G. And that gives you a map to the ith homology of connected Hurwitz space, where all these numbers remain the same except for the njth one. So the njth one now becomes nj plus 1. And then the statement is that this map is an isomorphism. Okay, so it's saying that there's this specific isomorphism between the homology groups of different Hurwitz spaces, and it happens when the number of branch points becomes sufficiently large, and it's sort of the number of branch points being sufficient in a linear way on this number I, which homology group you're looking at. Okay. Are there any questions about that?
What is the nature of the dependence of I on G?
So I is gonna go to infinity as the order of C goes to infinity, hopefully.
But like exponentially in the order of C, or
The proof gives something that's exponential. And yeah, but I don't know what the best thing you can do is, yeah. So. Right, so maybe what I'll say is that some very important cases of this theorem were already established by Ellenberg, Venkatesh, and Westerland. And so in the case when C has the property that C intersected with any subgroup of G. So if G prime is a subgroup of G and C intersect all subgroups of G is either empty or a single conjugacy class. Then this result was proven, a similar result, maybe I'll say. Similar result was proven by Ellenberg, Venkatesh, and Westerland. And so, this condition is satisfied in a lot of important examples. For example, the Hurwitz spaces that are relevant in trying to understand the Cohen-Landstrom heuristics. And so they were able to use this result to prove a version of the Cohen-Landstrom heuristics over function fields when Q approaches infinity. And so, but there are a lot of examples of Hurwitz spaces that don't satisfy this condition. So for example, the most classical Hurwitz spaces that were considered, are the Hurwitz spaces that parameterize simply branched covers of degree n. And so that's the case where G is the symmetric group and C is the transpositions. And this satisfies. So this is called they call this the non-splitting condition. And this satisfies the non-splitting condition if and only if n is less than or equal to 3. So really, even for S4, it wasn't known before that the stability is true. Okay, for S4 with transpositions. So that's that. So the second part of the theorem is that we can completely compute what the stable value is after inverting finitely many primes, namely the order of G. And also when all of these numbers are sufficiently large. So the second theorem is that, let's see. So the second theorem is that if Nj is at least this number for all j, then there's this comparison map. So I told you there's this comparison map from these Hurwitz spaces to configuration spaces that just forgets about the G cover. And what we can show is that on each component, that map it's an isomorphism in the stable range. So namely, if you choose a component Z, which is inside this connected Hurwitz space, this is a component, a connected component, then you can look at the homology of Z with coefficients in the integers adjoint 1 over the order G. And that maps isomorphically onto the homology of this configuration space of points 1 A, coefficients of Z adjoint 1 over P. Okay. Any questions about that?
Why should such a statement be?
Right. Well, I'm going to tell you something about, okay, why should this statement be true? Or that statement? Okay, this one. Okay, so this one. So I guess. So here you're stabilizing in all directions. So you have a lot of branch points in every conjugacy class. And so, but sort of the reason this is true is because when you have a lot of branch points in every conjugacy class, by moving things around, you can sort of get between any two different arrangements of different monodromies. Okay, maybe what I'll say is that to compute stable homology, what you can do is you can try to understand. There's this theorem called the group completion theorem, which tells you that if you want to understand, if you have some topological monoid and you want to understand the homology after stabilizing in all directions, you can do that by trying to understand the de-looping, the classifying space of that monoid. You can try to understand the homology of the classifying space of that monoid. And so what you end up trying to prove is that the classifying space of the monoid that's the Hurwitz space has the same homology after inverting the order of G as the classifying space of the configuration space. And the reason that's true is because, it has to do with the fact that the action of G on the conjugacy classes is on each individual conjugacy class is transitive. And so it's sort of, once you take the classifying space's homology didn't actually see the difference between any two elements in the conjugacy class. I don't know. I wasn't intending on talking about the proof of this one, so I don't know if I want to say more than that. We can talk afterwards if you want to know. So the thing I really, maybe what I'll say is that this one was sort of already known. It was sort of already known that if you were able to prove this theorem, then you'd be able to prove this theorem. And so really the main thing that I need to explain to you is why this theorem is true. And from this theorem, it was sort of already known how to extract that. That helps a little bit. Okay, so okay, maybe what I'll say is that one thing I forgot to say is that sort of in our earlier work, with Aaron, we proved the above result for the non-splitting case. And so the point here is that this is really some very general result, which has no restrictions on what kind of groups are allowed. Okay. So I'm going to start telling you about the proof, maybe. Right. So here's roughly the reason why. Here's roughly the reason why this non-splitting condition came up for Ellenberg, Venkatesh, and Westerlund. The reason it came up is that the whole Hurwitz space. So we're only interested in the connected Hurwitz space having homological stability, but the whole Hurwitz space has homological stability, so this kind of theorem is true for it. Stability. If and only if the non-splitting condition is true, roughly. Okay, maybe for a single conjugacy class. So K equals 1. If and only if the non-splitting condition is true. The point is that, we weren't really interested in the Hurwitz space. We were interested in the connected Hurwitz space. So this is not really, yeah. So hopefully you would have a proof that didn't actually care about whole Hurwitz space, but just about the connected Hurwitz space. And so I want to first reinterpret. So to begin telling you how the proof works, I want to first reinterpret what does it actually mean to have this kind of theorem be true, right? So let's reinterpret what this means. So you can look at. So we're looking at the homology of these Hurwitz spaces. So instead of homology, I'm going to work with the singular chains of the Hurwitz space. You can take the chains of this Hurwitz space with integer coefficients. And we're saying something about the homology groups of this chain complex. But this chain complex is really a DGA. It's a differential graded algebra because there's a multiplication on it coming from the concatenation of G cups. And so saying that homological stability is true. So homological stability, which is this theorem that we're trying to prove, it's equivalent to the statement that if you take this chain complex, there's some operator U such that when you quotient out by it, and this quotient is really some kind of mapping cone, so it knows both about the co-kernel and the kernel of multiplication by U, then this has homology bounded in some range. So it has homology bounded in a linear range of degrees. Okay, because if the homology of this is bounded in some linear range of degrees, depending on the number of branch points, that's exactly telling you that before you quotiented out by this operator U had to be an isomorphism in some linear range of degrees, which is what this thing is saying. Okay. So this is the kind of thing that homological stability is saying. And so
Are we still talking about connected Hurwitz space or?
maybe, okay, so maybe I'll say homological stability of Hurwitz spaces, but really it's for anything. So I could put a connected Hurwitz space and the statement is still true. Yeah. This can really just be anything that you're trying to prove homological stability for. Okay. Okay, so maybe to make things a bit more concrete, let me let me tell you the kind of thing that Allenberg, Venkatesh, and Westerlund did. So what they did is they showed. So Allenberg, Venkatesh, and Westerlund, they showed that if you take the zeroth homology of this Hurwitz space, and then you quotient that by this operator. So I'm just going to take an ordinary quotient of a ring. This is just some ring. You take the quotient by the ideal generated by this element U. If this is bounded, so this is like a graded ring, so I want it to vanish in large enough gradings. They show that implies that they have some argument to show that this is also bounded. Okay? It's bounded in the linear range. Okay? So the first step of the proof is to take this strategy and replace a single operator with a sequence of operators that maybe commute with each other. So let me be concrete. I'll give a specific example. So the first example where maybe we're interested in is this example of the group S4 with transpositions. So let's take that. Let's fix B to be the group S4, C equals transpositions. And now what we can do is So how many transpositions are there? There's 6 transpositions inside S4. So I'll give them names, x1 to x6. We did the elements in C. And what we can do now is you can take Hurwitz space. So if you take Hurwitz space, and then you can take the chains of the Hurwitz space, and you can, instead of taking a quotient by one of these operators, what you could instead do is you could take an iterated quotient by these operators. So we show that this is bounded. So that in some linear range first. So when you quotient that by all of these elements. So you can think of this as some kind of causal complex where you first quotient that by x1 squared, then you quotient that by x2 squared, and so on. Yeah. And we first show that this is bounded in linear range because it's true at the level of h naught. So h naught with this modulo this ideal is bounded. And so the point is that the way we begin our proof, we prove something that is true for the whole Hurwitz space, namely this sort of weaker statement about this kind of causal complex being bounded, instead of like homological stability isn't true in the general situation, but this statement is true. Okay, and what is this statement roughly saying? I mean, homological stability is roughly saying that if you fix a degree and you let the number of branch points gets very large, then the rank of the homology is constant. And this kind of statement is saying that asymptotically, the rank of the homology is polynomial. That's roughly what this kind of statement is saying. And so now knowing that this is polynomial, first what you can do is you can try to translate this now into a statement about the connected Hurwitz space. And then you can try to analyze the leading terms of that polynomial and show that it wasn't just any polynomial, it was a constant polynomial. And that's homological stability. So let's try to do that precisely. So how do you do that precisely? So you can, so the point is that if you take this Hurwitz space, you can write this as a disjoint union over all subgroups of G of the connected Hurwitz space for G prime. And then you take the conjugacy class to be the intersection C with G prime, okay? So any G cover, if it's not connected, it's connected with respect to some subgroup of G. And so what this does is it gives you a filtration on the Hurwitz space as a module over itself. It gives you a filtration whose associated graded are connected Hurwitz spaces for smaller groups. And so by sort of induction on the order of G, if you know this statement, then you can prove this statement where you replace Hurwitz space with connected Hurwitz space just by using induction and the fact that you have a filtration. Okay. So induction on order of G plus a filtration argument using this kind of filtration, this stratification into different connected Hurwitz spaces, you learn that the chains on the connected Hurwitz space modulo all these things is bounded in a linear range. Okay, so this is not quite homological stability. Again, it's sort of saying that, it's saying that, HI grows as a polynomial of degree less than or equal to 5, and you really want to say it's a polynomial of degree 0. So how do you go about trying to show that it's a polynomial of degree 0? Well, let's say that you wanted to prove that, you can do this by induction, by sort of descending induction. So we first know that when you quotient out by all of these operators, it's bounded in some linear range. But via the discussion over there, knowing that when you have quotient by some operator, it's bound in some linear range, that's the same thing as saying that when you don't quotient out by the operator, this operator acts by an isomorphism in some stable range. So the point is that this statement is now going to tell you that if you take the chains on this connected Hurwitz space and you quotient out by just x1 squared up to x5 squared and not x6, that this has stability with respect to x6. So in other words, x6 acts by an isomorphism in some stable range. And so now, if you wanted to prove that this was actually bounded in some linear range, you just have to prove that the stable value is 0. That's all you have to show. And so now proving homological stability comes down to a question about computing stable homology. So, these two theorems are very closely related to each other, and that's in that way. So, right, so we need to show that when you take this connected Hurwitz space and then you quotient out by x1 all the way to x5 squared, and then you invert the last one, you need to show that that's 0. Okay. So how do you show something like that? So again, we're going to play off the fact that these Hurwitz spaces sort of are stratified into these different connected Hurwitz spaces. But there's a key input that you need. And let me see if I can describe how that works. The point is that you can consider the following thing. So there's a map from this. There's a map from, let's forget about the connected Hurwitz space for a bit. Let's just remove the C, okay? So let's just look at, sorry, there's a chains everywhere that I'm forgetting to write. Okay, so let's look at Hurwitz space. And then let's quotient out by all of these operators. Or what do I want to do? Okay, so the claim is the following thing. The claim is that you in this case, what you can do is you can try to prove that when you take the Hurwitz space and then you do this, you get the same answer, and then you invert the last one. So this is sort of what we're interested in. You can show that you get the same thing as if you were to take the chains on just a configuration space. And here you should think of the configurations as parameterizing covers where all of the monodromy is this element x6, the specific transposition. Okay? So I'm going to think about a configuration of points, but I'm really thinking about it as G covers where this is the monodromy of all of the points. So there's this configuration space, and you can do the same thing to this configuration space. You can quotient out by all of these elements, and then invert the last one. And the key thing that you need to do is you need to show that this map is an isomorphism, because the point is that this map is compatible with the filtration on both sides, and this side, all of the associated graded pieces of that filtration vanish, except for the one corresponding to, I guess, the one corresponding to just x6. But in particular, there's no part here that corresponds to a connected Hurwitz space because all of the monodromy isn't just x6. And so this, the point is that here the irrelevant associated graded piece is 0, and here the relevant associated graded piece is that. And so if you can show that this maps an equivalence, then you've shown that this associated graded piece has to be 0. Okay? And so you have, so you have to show this, okay, and how do you show something like that? How much time is there?
5 minutes.
Okay. That might be enough to say a little bit, okay. So how do we do this? So let's think about this, let's just call this M, okay? And let's call chains on the Hurwitz space. I'm going to call that R. And then that has some map to this chains on the configuration space, which is the one ultimately inducing this map. I'll call this S, okay? So these are some differential graded algebras. And this map is actually just the map that's M mapping to M tensored over R with S. So this is some module over R in some differential graded sense. And this is sort of some relative tensor product in some differential graded sense. Okay? And so you're really trying to show that when you base change this module to this other ring, it didn't change the module. Okay, so how would you show something like that? So here's sort of a key proposition. So suppose that you have a map, let's call it F, R to S, a map of connective, so they don't have negative homology groups, DGAs, and let's say it's a surjection on H naught. And let's say that it has some module M. And let's say we have some ideal inside H naught of this DGA. It's a usual ideal acting nilpotently on each homology group of it, let's say. Okay. So then maybe I want this to be connected also. So then the statement is that if, let's say, H naught of R mod I is the same thing as H naught of S mod I, then, and this is usually not a difficult condition to check, and the following relative tensor product is the same. So the relative tensor product of this maps isomorphically onto the same thing if you did it for S. Then, in fact, M maps isomorphically onto this relative tensor product. Okay. So how do you prove something like this? Maybe I can say it's not that difficult. It really just, it comes down to a descent kind of argument. So you have the map from R to, there's a map of rings of DGAs from R to H naught of R mod I. And you can form the check nerve of that map. And then this condition about acting nilpotently tells you that M is the limit of this check nerve, and this is also the limit of the check nerve. And then these two conditions are exactly telling you that at every stage of that resolution, the map was an isomorphism. Okay. So, I mean, you can roughly, I like to think about this as saying something of the form, if you have a map of varieties and it's a bijection on points, and it's also an induces an isomorphism on cotangent complexes, then it's also just an isomorphism of varieties. And some statement of that form. So, okay, so we apply this in that situation. And the point is that now you have to prove, the key statement you have to prove is this statement. And I think I'm kind of out of time, but I'll just say that this statement comes down to a really explicit computation at the level of spaces, where there are two spaces that you need to show are homotopy equivalent, and you can just write down a homotopy equivalence between them. it's just a very explicit homotopy equivalence. Yeah, that finishes it. And maybe to finish, I'll just say, I hope one of the takeaways from this talk will be that, homotopy theory, the perspective of homotopy theory really has a lot to offer in thinking about these kinds of moduli. And the other point I want to make is just that I think our homological stability results will be very useful to people who want to prove things in arithmetic statistics over function fields. And so, yeah, that's it.
Any questions to the speaker?
If you want to prove things over number fields eventually, like how much insight does this give you besides something to, like, do you get a path to anything?
So the key thing I think the key thing that's sort of missing from trying to run a similar strategy to proving these conjectures in the number field setting is something like the Grothendieck-Lefschetz trace formula. I don't know of anything that would allow you to run a similar strategy in the number field setting. One thing I can say is that there are a lot of things that we learn about the number field version of the conjecture from thinking about the function field version. So, for example, I mentioned that Tur-Kelly found sort of the explanation for these counterexamples in the number field setting, and that sort of led to his prediction to sort of closer to the actual answer. But yeah, I don't really understand that. Maybe somebody else here knows. I don't know.
Could you say a little bit about the shape, this homotopy equivalence, like?
Yeah. So the space that you have, the space of these two sides. So the left-hand side roughly looks something like, it looks something like you have this sort of strip, and then you have some integers on the left and like labeled on the left and right side of the strip. And then inside the interior, you have a bunch of points, which you should think of as some kind of G cover, and they're labeled by elements of this conjugacy class, but there's some rule about if you move them around, then they might conjugate in some way. And so what you need to show is that, in this case, what you need to show is that if there's at least the space of points where there's at least one element that's not x6 inside the interior is contractible. That's what you need to show. And the way you do that is you do this sort of algorithm where you look at the first point, which was not an x6 from the bottom up. And so in this case, it'd be x1. And then you do something funny where you pull a label out of the boundary, which is something you're allowed to do in the space. And maybe this label gets changed to n-1, and this you pull out some point in the boundary, which is labeled x6, and then you move it across here. And when you move it across, when you move it over something, this label gets conjugated. So maybe now it turns into something like an x4, and then it might move past the x6 and get conjugated to like an x5. But then when it hits the right-hand side of the boundary, it's no longer x6. And because it's no longer x6, you actually end up at the base point when you hit the boundary. And you can do that. You can check that this construction gives you continuous null homotopy of that space. Yeah.
A wild case, do you have a guess as to what is true and does the method work?
Yeah, so the place where the method breaks at the moment is that the Hurwitz spaces are no longer finite tall covers of configuration space. And so you don't have this comparison, for example, between the L-adic cohomology and the singular cohomology anymore. I mean, in principle, you could just try to study the L-adic cohomology of those Hurwitz spaces. But I don't know, like, there was some, in this part of the argument, in this, especially at this step of the argument, there was like in the construction of, in the fact that we have this model as a space, that is something that really is using the fact that we're over the complex numbers. And so I don't know a way in the not tame setting to do similar arguments.
Do you think that explains the counters, the difference between the number field setting and the function field setting? Because in the number field setting, you're somehow forced to consider wild.
Which difference are you asking about?
Maybe the fact that
Tur-Kelly.
Tur-Kelly's thing is wrong.
Oh, that, I don't, oh, sorry, there you go.
I mean, there's a sort of these local, these like Brouwer-Mannion type abstractions in the number field setting. That's my vague understanding of this. But so there's some sort of local global abstractions. It might be related to what you're saying. Yeah, I see your point though. Yeah. Not sure.
I mean,
That's the
the,
medicine.
yeah, the counterexample is because the cyclotomic extension is ramified in the number field case, and it's not ramified in the in the number function field case. But the ramification is sometimes tame, so I don't think wild ramification is crucial to the counterexample.
You're saying like even like a p cyclotomic extension would.
Yeah, I mean, I think the counterexample, well, I mean, uses the Z-mod 2 cyclotomic, which is wildly ramified, but I think you can do it with a p cyclotomic, which is not. If anything. It's, yeah, I don't think it's really close really to wild ramification. It's a different property.
Cool, thanks.
So how do you rate the eigenvalues of Frobenius from this isomorphism?
Sorry?
How do you rate the eigenvalues of Frobenius?
Right. So it turns out that if you just want to prove these results for Q sufficiently large, you don't need to. You don't need to understand much about the Frobenius. And the reason is that, so if you think about the homology, the homology, if you have a lot of branch points, the homology in low degrees is the same as the stable homology. And it's the same as configuration space where we know the eigenvalues of Frobenius. And in large degrees, the absolute value of the eigenvalues of Frobenius is pretty small. And so as long as the cohomology is not too big in large degrees, that's not going to be the main contributing term. And so sort of Delen's bounds on the eigenvalues are sort of good enough to say that if Q is sufficiently large, then it doesn't matter. And so if you wanted to prove this result for all Q, then you'd have to actually understand the eigenvalues of the Frobenius on the unstable homology or unstable cohomology. And I know how to prove that the unstable homology grows exponentially at like a lower bound that's exponential in a way that depends on the order of the group. And so that tells you that these topological results are not enough, and you really do have to understand something about the Frobenius if you want to prove it for very small Q.
Do you think it's true for small q?
That's the thing. I think the fact that I am, what's the word? Agnostic? Okay. I'm agnostic. I think.
Is there numerical evidence or?
I mean, okay, it's proven for, let's see, like we know how to count maybe S3 covers and yeah, there are examples where we can prove everything, but maybe those examples were small enough that it didn't matter. Yeah, maybe those are just examples where it wasn't. So
Are those examples where the unstable cohomology is already growing exponentially, and then there's
yeah, I mean
there is some miraculous cancellation of those countries?
Yeah, but it might also be just because in those examples, it's pretty close to some kind of twisted configuration space. It's a very simple.
So the unstable cohomology is like showing up in pairs that cancel in some sense, or?
Yeah, so for example, in the case of S, I think that's something I'm very interested in trying to understand. So like in the case of S3 with transpositions, I think in that case, the sort of things about point counts are known. So for example, Davenport and Heilbronn did it over number fields, and I think somebody else who I don't remember did it over function fields. And so we know the point counts are the thing that you should expect. So there has to be some kind of Frobenius cancellation in that example, but that also might be small enough that it was growing exponentially, but not fast enough exponentially to actually cause a problem if there would have been a problem. So I think it's reasonable to believe the conjecture, but there isn't a lot of strong evidence, I would say, but maybe somebody else knows. I don't know. Yeah, but that's something I'm very interested in trying to understand is what is the Frobenius action on the unstable cohomology? Because it would have to cancel out. It's sort of too big to not be something you don't have to be something you don't have to think about.
Any other questions to the speaker? Great, we have no questions. Let's thank the speaker.